Good morning, children. Welcome to all of you in the physics class. Today I will explain the chapter vibrations of stretched strings. That is given here. Now, moving forward, first of all, we have to discuss in this chapter the stationary waves in strings, fundamental modes, and harmonics. Okay. Now, what is the speed of transverse waves in a stretched string? What is a stretched string? Stretched string is nothing but it is uh, tied between two rigid supports and have the lot of tension. Then you can say that it is a stretched mode. Okay. So a string means a wire or a fiber which has a uniform diameter and is perfectly flexible, that is, which has no rigidity. In practice, a thin wire fulfill these requirements approximately. So, the speed of transverse waves in a flexible stretched string depends upon the tension in the string and mass per unit length that is given in this formula. The speed of transverse waves of a stretched string have the formula V is equal to under root T by M, where T is the tension in the string and M is the mass per unit length. If we put here the formula of mass, that is volume per unit into density, and normally the string is cylindrical form, so it have the volume pi r square into 1, because we have the take here 1 meter length, density is d, so we get here mass is equal to pi r square into d. So speed of transverse waves becomes v is equal to under root t upon pi r square into d. Okay, this is the formula. Now, vibration of stretched string, how can we explain it? What is the vibration of stretched string? In the last chapter, I have explained about the vibration of air columns that produces musical sounds like flute, that is also called bansuri, whistle, bugle, clarinet, etc. All are the musical instruments that are air column instruments. In addition to these, there are other musical instruments like sitar, like sarangi, like violin, like guitar, like sarod, like veena. All of have the musical instrument that have the string. Okay, and this string is actually a stretched string. So here also we find the formula V is equal to under root T by M, where T is that tension and M is the mass per unit length. Now, by the principle of superposition of the incident and the reflected waves that are produced, that is shown in this diagram, there are two ends that are rigid end and creates the nodes, and becomes middle point creates the antinode. Okay, so what happened here? We know that the distance between two consecutive nodes is lambda by 2. Okay, where lambda is the wavelength. Hence, if L is the length of the wire between the clamped ends, then L is equal to lambda by 2. Okay, so now moving forward, lambda is equal to 2L. If N is the frequency of vibration of the wire, then we get here N is equal to V by lambda is equal to V upon 2L. Now moving forward, so after putting this value in the formula, we get N is equal to 1 upon 2L under root T upon M. If you want to show, then back and find it, because this is the formula which are used here. This is the frequency of the note emitted by the wire. Okay, so this is the formula of the frequency. Frequency of the sound emitted from a stretched string can be changed in two ways. This formula shows that what is the two ways? that is it's have the dependency of two terms, that is tension and that is mass. So it can be changed by these terms. Okay. Now moving forward, laws of vibration of stressed string. What is the law? There are three fundamental laws of transverse vibrations of a stressed string. First is law of length, second is law of tension, third is law of mass. Now, what is the first law? Law of length. Because frequency is inversely proportional to the length, so multiply of both the terms n into L is equal to constant. Okay. In the same way, law of tension, the frequency of the waves is directly proportional to the square root of tension. Okay. Now, third law, law of mass. So, frequency of the waves is inversely proportional to the square root of the mass. Now, next point is stationary waves in a string fixed at both ends. Mode of vibrations. Let us consider a uniform string of length have the length L stretched by a tension T between two fixed points at x is equal to 0 and x is equal to L. Then what happen here? Let a harmonic progressive wave be set up in the string by plucking. This wave gets reflected from the two fixed ends of the string continuously, and as a result, by principle of superposition, stationary waves are formed in the string. So, if the incident wave have the equation y1 is equal to a sine omega t minus kx, okay, as there is a phase change of pi after reflection at the fixed end of the string, the reflected wave traveling from right to left, that is in the minus x direction on the string, is represented by y2 is equal to a sine omega t plus kx plus pi. So we get here minus a sine omega t plus kx. According to the principle of superposition, the net displacement y is equal to y1 plus y2. After putting the value of y1 and y2, we get here, after applying the trigonometric formula sin a minus sin b, we find y is equal to minus 2a cos omega t sin kx. Okay. The argument of trigonometry function in this equation are not of the format of omega t plus kx. Okay. This is very important. Not of the form of omega t plus minus kx, because these have two terms, a sin omega t plus ks minus sin omega t minus kx. So we get here minus 2a cos omega t sin kx, not in this manner. So in fact it represents a stationary or a standing wave, and this equation shows stationary wave. So what happened here? At the end of the string at x is equal to 0 and x is equal to L, where it rigid boundary are fixed. So what happened here? Y is equal to 0 at x is equal to 0 and y is equal to 0 at x is equal to L. So according to the diagram that I have already shown here, in this diagram here node and in the midpoint antinode. So applying the second condition, equation number third, we get this equation or this. So 0 becomes sine 2 pi L upon lambda. So this can be also written here, 2 pi L upon lambda is equal to p pi in the angular format. So what happened here? If we get the value of p is equal to 1, 2, 3, lambda becomes 2L upon p. So this is the general formula of wavelength of the stationary wave when it is fixed from the two rigid ends. Now moving forward, first are fundamental mode of vibration that are explained by this first diagram, where node and in between antinode the length is L and is equal to lambda 1 upon 2. So first our fundamental mode of vibration, when P is equal to 1, we get from the above formula L is equal to lambda 1 by 2, Rn is equal to this. So what happened here? The frequency N1 is equal to 1 upon 2L under root T by M. This is the fundamental frequency of the first harmonic of the string. The sound note produced by the string is called fundamental tone. Now moving forward, second mode of vibration, where the lambda 2 is the frequency wavelength of the standing wave set up on the string corresponding to value of P is equal to 2. Then we get lambda 2 is equal to 2L by 2, L is equal to 2 lambda 2 upon 2. From above equation, the frequency of the value of the string N2 is equal to 2 upon 12 under root T by M, that is 2 times N1. So we get, in case of the tone emitted from the string is twice of the frequency of the fundamental tone. This tone is called the first overtone or second harmonics. Now moving forward, similarly the third mode of vibration, where the wavelength is lambda 3 and the value of lambda 3 becomes 2L upon 3, that is L is equal to 3L3 lambda 3 upon 2. After putting the above formula, we get the frequency value N3 is equal to V upon lambda 3 or 3N1. So this is called the frequency of emitted tones in 3 times the frequency of the fundamental tone. This tone is called second overtone or third harmonic. This is very important for you. So we can say that the string is made to vibrate in 4, 5 ... segments. Then still higher overtones can be produced. If the string vibrates in P segments, then frequency becomes N is equal to P upon 2L under root T by M. So finally we can say that the frequency of the fundamental tone and the overtones of stress string have the following relationship: N1 is to N2 is to N3 is to N4 is equal to 1 is to 2 is to 3 is to 4 ... So the frequency are in harmonic series, hence these tones are also called harmonics, because the series is harmonics. The fundamental tone N1 is the first harmonic, the first overtone N2 is the second harmonic, the second overtone N3 is the third harmonic. The tones of frequencies N1 and 2 N1 and 3 and 5 are the odd harmonics, and the tones of frequencies N2 and 4 and 6 are the even harmonics. Clearly, stressed strings have both type of harmonics. Position of nodes can be determined by this formula. In stationary waves, modes of position of zero displacement, there are 2 nodes in the first mode of vibration, 3 nodes in the second mode, 4 nodes in the third mode, and so on. Therefore, in the pth mode of vibration, there will be P plus 1th nodes. They are located from 1 into the string at distances. So after putting the value of this x is equal to 0, L upon P2, L upon P3, L upon P ... L. For example, in the first mode of vibration, where the value of P is equal to 1, the nodes are at x is equal to 0 and x is equal to L. In the second mode of vibration, where value P is equal to 2, the nodes are at x is equal to 0, x is equal to L by 2 and x is equal to L. So in this manner, we also calculate the position of antinodes. In a standing waves, antinodes are position of maximum displacement. There is one antinode in the first mode of vibration, 2 antinodes in the second mode of vibration, and so on. So distances from one end of the string are x becomes L upon 2p, 3L upon 2p, 5L upon 2p, that is 2p minus 1 upon 2p. For example, in the mode of vibration P is equal to 1, the antinodes is equal to x is equal to L by 2. In the second mode P is equal to 2, the antinodes are x is equal to L by 4, 3L by 4, and so on. So we can say that where the value of P is equal to 2, so there are 2 antinodes generated. Now moving forward, this is the instrument that can be used in the practical purpose. and this is called Sonometer. This is the practical instruments. It can be better understand in the lab. You have to learn only the formula. By using this, we can calculate the frequency of the given wire, that is n is equal to 1 upon 12 under root T by m. In this manner, we can conclude this chapter. Thanks a lot to watching this video. Thank you all of you.